Okay, our speaker, Professor Sivan Toledo from Tel Aviv University. The talk of his title is Research to Teaching and Book to Research in Location Estimation. Thank you.
Okay, thank you, Yadid. Thank you, everybody, for coming, for attending. So Yadid already gave cited the title. So I'm going to tell a story that's not new, that's repeating over and over. At least some of us go through this process of doing research, of moving to teaching, and then discovering through teaching or through writing that there is more research to be done, interesting, and so on. And I'm going to talk about this in my particular framework, a particular story, which is in location estimation. So it starts with, okay, so just, why is this not flipping? Okay. So I'm going to first tell a quick going through the story. Then I'm going to tell you more about the book and the course that I've developed. Called the book is called Location Estimation from the Ground Up. The course, for an obvious reason, has a weird name. And then I'm going to tell you about two research problems that emerged not from the original research, but from the teaching and writing that I did following the original research. One is a problem. I hope that these two problems will be interesting on their own. One is called the cocked hat problem, and the other is about GPS localizations or GNSS localizations without timestamps. Then I'll offer some higher level reflections, some of my thoughts about what happens when you go through this process and what I've learned both from the overall process and also from the specific course that I've been teaching. So the original research is a project called Atlas. It's a wildlife tracking system that I've developed starting in 2012. So it became operational in 2014. So it's been running for active running for 6 years. In development a little bit before that. And what you can see here is you can see that it starts with small tags, electronic components that are attached to wildlife. Here, the example is a small insect-eating bat, and the black epoxy enclosed thing you see on its back is one of these tags that's glued to the bat's back. And then the signals from those the tag is a radio transmitter. Signals are received by a base station. What you can see is a cellular base station, but on top of that cellular base station is one of our antennas. And when 3 or 4 or more base stations pick up the signal, we can generate localizations. And what you can see in the middle is a bunch of tracks. I think this is an owl going back and forth between several locations, several hotspots. But I've already talked about this in this colloquium a few years ago, so I'm not going to give any more details about this. This is just the context. A system for tracking wild animals, especially small birds and bats. Initially, still talking about Atlas, the effort consisted of a huge amount of system building, designing hardware, testing the hardware, writing software and firmware, testing them, developing algorithms, testing them, making sure that everything works together. A lot of kind of engineering or system building efforts. There was also some research involved, which was what attracted me to this. This was not a trivial or easy problem to solve. There was some research on algorithms, some research on developing the tags, how to develop the tags, the hardware, research on batteries, and that led to several papers. Again, systems paper. The systems paper had some algorithms in it in ISPN, in a sensor network conference. But there were also papers about the tags, about the software structure, about testing, how to test batteries and what they perform like in those small devices. So there was a lot of system building, some research, kind of very varied areas, not very focused. And in terms of the effort, also a lot of support to users who set up systems. There are now 2 active systems in Israel. There was another one that was put up and then folded, was not really useful. One, a very large system with I think, over 20 base stations in the Netherlands, one in the UK near Exeter, one in Germany, another one in Mauritius that's being set up by Israelis or Israelis in collaboration with locals. And the users need technical support. Now they need less as time goes by. They learn to use the system. They learn its quirks. They learn to communicate with me. But initially, this was a lot of effort. So once the system is up and running, you discover, of course, that the research and the system building generates more research. That's kind of obvious. That happens to all of us all the time. We do research, and then through research, we discover new problems. There's nothing new in that. Here, the research was on clock synchronization, how to compute these localizations when the clocks of the different base stations are not tightly synchronized. So we developed an algorithm to synchronize them in software as opposed to synchronizing them in hardware. Tags that transmit in a different modulation that allows for more accurate localizations. A lot of work on putting sensors on the tag so that they collect data, especially acceleration data from the animals. Also environmental data, air pressure, mostly to get the height, how high they fly. And this also is leading now to ecology research papers that I sometimes contribute to. My contribution is usually the technical contribution of making those systems work, but it's still a contribution. The first paper just got published using so this is a picture. The image is from the paper. The paper is about owls in the Hula Valley. Different ecological associations that are not relevant to this talk, and I don't find particularly interesting. And there are more papers in the pipeline, more ecological papers in the pipeline. Again, it's not research that I feel is enriching to me or important to me, but I'm obviously delighted to see that my research is contributing to research in another area that I care about. Okay, so that was kind of obvious. And then things evolve, life goes on, life happens. And somebody asked me to teach a class. My department chair asked me to teach a class and also to write a book. It was not the same person. So my department chair asked me to teach a class, and somebody else, one of my colleagues, asked me to write a book. He was the editor-in-chief of a book series, put me on the editorial board of the book series, and said that my responsibility is either to bring two books to the series, two good books, high-quality books, or to write one. So what do? You have multiple choices, and they're reasonable. They're good choices. So you can teach again a course that you already taught, maybe the last course you taught, the one before that if you've been in the university for a while, or you can copy a good course from somebody else. And I've done both of these, and they sometimes work well. I once copied a fantastic course in numerical in algebra from somebody. I enjoyed teaching it. It was relatively easy to prepare because I got all the materials from somebody. It was a good course. Everybody benefited. With respect to the book, most people just say no, so you can say no. Or you can write a book that I labeled here as yet another. What I mean by that is that you take a template, a topic that's already been developed, and there might already be books on it, but they're not perfect to your liking. You think you can improve on them, you can expand on them, you can narrow them down and make them more, and write a book that's more focused. Or that exposes more of your special expertise and so on, but still, again, the structure is fairly clear. So these are all valid choices. There are other choices, and in this particular case, I took the two bold choices. I decided to develop a completely new course. I felt it would be boring to do one or two again. And I decided to write a book that would have a novel scope and a novel approach, which is another possibility. So let me tell you about these, about the new course and the new in the book, and how that came about. And the first thing you discover after you say yes to one of these people is that you don't know what they are about. I mean, sometimes, especially if you write a book, you might have a very good idea of what the book is about. I didn't really have a very good idea of what the book would be about. And I certainly did not have a good idea of what the course would be about. And I didn't have a good idea because to build Atlas, to build this system, I used expertise in a range of different areas, some of which I was an expert on, some of which I learned, some of which I learned to the extent that I could do something, but I never became a real expert that generates original research. And these areas are location estimation, embedded systems, hardware, software, the implementation of estimation algorithms. There is some RF hardware that I worked on. There is signal processing that happens before the estimation, how you implement the signal processing. And I do research. For example, my most recent paper now is about parallel implementation of the signal processing to speed it up, to increase the throughput of the system. But it's, again, signal processing implementation, you have to do it. And it is an opportunity for research if you do research on high performance computing, for example. Data management was something I did. I'm not an expert on. It was, for me, a kind of a programming or an engineering task. But other people could take it into something more interesting research-wise. Other people could also look at maybe the system design, the interactions, and so on. So what's the book about, and what's the course about? And at least for me, the first kind of reaction was that if I needed all of these little bits of expertise to build a useful system, then the students should also have this kind of expertise. But really, the initial tendency, and I think that also happens in courses that are not motivated by systems, is to teach what you know, kind of define the scope of the course of what you know in your area, not what you know in general, but what you know in a particular area, and say, that's what I want to teach students because that's useful to me. And that's certainly, if you build systems, that's not a good way to go about this. It gets too diffuse. It's eclectic. I mean, this cloud of topics that I showed you to show you that it's eclectic and that it doesn't work well as a course. It's not focused, and it doesn't cover any coherent body of knowledge. So you can maybe teach the students the system building skills or skills of putting things together, but what they learned at the end of running through an exercise like this, it's not clear that they learned something useful. So really what you have to do is you have to look at this and you choose a coherent subset that would make for a good course. And really what I have here in the sidebar is that really in the university we teach different skills in different courses separately, even if you need all of them to use all of them or multiple skills together to do something useful professionally. So, but we still teach them separately. There are some disadvantages to this, but the courses are coherent. They can be deep, they can be broad. It's better than taking a course and saying, okay, I'm going to teach what students need to know in order to build X or Y or Z. Okay, so I need to choose a coherent subset. So what is the book about? The book is called, like I said, Location Estimation from the Ground Up. And it's really about location estimation. How do you go from measurements of angles, distances, time of arrival into locations or maybe multiple locations in a map? And it's location estimation for computer science and math majors. In the course, in the classroom, there were also EE majors, electrical engineering majors. There were grad students from math, from computer science, from electrical engineering. I think they benefited from all of those groups benefited from the course, but the course was really designed as a course in location estimation for computer science and math majors. There are courses similar to that, not quite like that for EE majors. They're, I think, not accessible at all to computer science math majors. So this is what I decided to build a course around, and eventually that evolved. The lecture notes evolved into a book. I should also say that when the book's title is kind of indicative of what's between the covers. The course title is not, because the course title you have to give it when the course is listed in the course catalog. And at that time, I didn't teach the course even once, and I actually wasn't sure exactly what the course would actually include. So the course has a slightly weirder name. The course has a slightly weirder name. But that's it. So what is the course about, apart from the topic? It's really about two things and some supporting material. The two things are modeling and algorithms. And the scope, what defines which problems we model and which algorithms we teach to solve them, is a variety of least squares problems. They're all in location estimation, but these algorithms and to some extent the modeling is also useful in many other areas that involve estimation. And also some supporting topics. So let me first tell you about the modeling, how these different, or this variety of least squares problems translates into modeling problems and into algorithms. So on the modeling side, for linear problems, it's actually quite difficult to find real world estimation problems that are linear. But I found one. There is one. It's called in location estimation or mapping cartography. It's called leveling. I won't go into it, but it leads to a linear least squares problem. Then I teach students to model mildly nonlinear problems. When you model them, you don't know that they're only mildly nonlinear. I mean, you can have some indications by the number of by the degree and the number of unknowns, but they're you look at the functions that you want to minimize, and you find that they're only mildly nonlinear. And that's location from time of arrival, GPS localization problem, the Atlas transmitter localization problem. The equations are basically the same. Angle of arrival localization problems. So these are mildly nonlinear. Then there are highly nonlinear least squares problems, like estimating the arrival time of a signal from a satellite. It's also a least squares problem, but highly nonlinear. Then there are dynamical systems. Dynamical systems are systems that depend on time, and you want to estimate the state at different times. And the kind of modeling that I teach there is Kalman filtering and Kalman smoothing. And then there are mixed integer least squares problems. And the one I teach is called RTK, estimating locations from carrier phase information. I'll explain what it is towards the end of the talk, so I won't explain it anymore now. In terms of the algorithms that solve these models, in the linear case, there is QR factorization, cholestive projections, the SVD. For mildly nonlinear problems, the algorithm that actually, or the family of algorithms that people actually use to solve least squares is Gauss-Newton, but I also explain to some extent gradient descent, Newton, derivative free metals like Nedler-Mead. For the highly nonlinear problems, you have to do grid search, and grid search for time of arrival translates into cross correlation, and cross correlation translates into FFT. For dynamical systems, it's the Kalman filtering. The way I teach it is as a specialized sparse QR solver. And the mixed integer solver or algorithms are a combination of a lot of the things that the students have seen before, plus some new ones. So it's again a QR factorization or QR factorizations, a specialized branch and bound algorithm that's called Schnorr-Juchner, and then LLL, the lattice basis reduction. I also teach about outliers and an algorithm that can deal with outliers. It's called RANSAC, or a methodology that can deal with them. Most of them I teach, and the book describes to the last detail, to the point where you can implement them. There are implementation exercises in the book, in the course. Some of them that are really too difficult or too complicated to explain fully in a course or a book that's on something else, like the SVD. These are still explained with all the details, but a relatively naive version is explained, not the most efficient version is explained. And then the supporting materials are localization systems. So I tell readers how these measurements are generated. So the estimation is you go from measurements to locations. How are the measurements made? So you have to tell them something about this. and then what statistical explanation for y least squares, and again the same explanations like maximum likelihood would also explain why you might want to solve problems in L1 norm if that's what the distributions are for. Distribution free or estimators like blue, and then again outliers, which are important to emphasize to students that even if you assume that things are Gaussian and so on, not all the measurements are going to obey those assumptions. And then also very importantly, a posteriori covariance estimation. So making sure the students understand that they need and can estimate how accurate the solutions are. And also a priori bounds, the bound I teach is called the Kramer-Rao lower bound. It's an important bound for estimation for statistics. And I show how to use it. It's important not only from the statistical point of view, it's also important when you build systems, because you build the system to try to make this lower bound as good as you can in terms of placing the satellites in space or placing the base stations around the region. These are decisions that are governed by an information theoretical concept, which is called this Kramer-Rao lower bound. So I teach it too. So most of the course is again about modeling and algorithms, but it cannot be taught, I think, in isolation. So these supporting ideas are also taught to the same level. So that's what the course is about. If you want to skip this laundry list of topics, it's about classical deterministic estimation as opposed to Bayesian estimation. And what's important is in a context that only requires elementary geometry to understand. So classical estimation is everywhere in science and engineering, because most of the measurements that we make of distant galaxies and their redshift and how the Big Bang happened, whatever, or what happens in chemical reactions, these are measurements. We're trying to measure quantities that we can't observe directly. We can't measure directly. We measure something else, and then there is a rule that links the measurements to the quantities that we are interested in, and we need to estimate them. In most cases, so these are important computations, but in most cases, to understand the modeling, you have to know something about physics, about astronomy, about chemistry, about biology, and so on. So it's really not accessible to our students, at least to students that are not in double majors, specific double majors. And this problem is a problem where where the students, our students, computer science students, can understand everything, because all the background that's needed is just elementary geometry, maybe a little bit of trigonometry. That's it. Okay, so that's it for the first part. I started from research, went to a book and a course, but then that generates more research. So now let me tell you about this additional research that came out of the book and course projects. And I hope at least the first part is supposed to be mostly entertaining. I hope you'll enjoy it. Okay, so the problem is called the cocked hat. Cocked hat is a hat, so is a hat that's screwed or crooked, sitting crooked, and I think that was the name was given because that was because French Marine officers used to wear hats like this or something. I should have put a picture in the presentation, but I didn't. And it's a problem. The context is, I think, really cool, and I'll elaborate all the details. It's a problem that pretended to be a homework problem for the course and for the book. I learned about this, discovered that there is this problem. I said, okay, this is going to make a wonderful homework exercise, but then I couldn't solve it. So it turned out to be into a research project. So what's the cocked hat? So you're a marine navigator, and you're out at sea, and you see three landmarks on shore, maybe lighthouses or hills. You identify them, you know where they are on a map. You measure the azimuth, the bearing to these locations, and you draw a ray with the corresponding angle, corresponding azimuth from the location, from lighthouse A to where the ray is pointing, to lighthouse B directly south, because you saw lighthouse B directly north of you, and from C and so on. Now, if you take only two measurements, then they'll intersect at a point, and then you'd say, okay, I'm at this point. You know that that might not be exactly right, because if you made if you made angle errors, then this would move the point, but you don't have any estimate that's better, so that's it. But marine navigators were taught, at least starting in the 18th century, to make 3 measurements, if at all possible. And when you make 3 measurements, usually they don't intersect at a point, but they form a triangle. And navigators called this triangle the cocked head, because it looked like the head of their officers, the captains. And navigators and the people who taught navigation started to try to figure out where is the shape relative to this triangle, where is your belt. So that's the cocked head problem. And so the problem in the name probably goes back to the 18th century. The first time it appears in some sort of a formal description of what's going on is in this book from 1938. It's a British Admiralty navigation manual. It's a textbook from which the British Navy used to teach navigation to navigators. It's volume 3. It's a book that's important. It's a book that's full of geometry, trigonometry, and proofs. It's not a story. It's not about drawing lines. It's the volume 3 is about the theory of navigation, proofs, geometry, trigonometry, and that's where this cocked head result or insight first showed up. Now, what's the insight? This is the insight. The insight is you model the errors, so you give the errors names or letters. So F is the true position of the ship. But the angle that you measured to A is actually has an error, and the error is epsilon1, at B epsilon2, at C epsilon3. And now you want to say something about the triangle as a function of these errors. And what they discovered is that the chance, that's actually, the statement is made incorrectly. I'll explain this in a second. But what they discovered is that the probability that the triangle contains the ship, if the signs of the angle error, of the error angles, epsilon1, this epsilon1 can be clockwise or counterclockwise with the same probability, then the probability that the triangle contains the ship is only 1 in 4, 25%. They actually phrase this as a probability as opposed to likelihood. That's an incorrect statement. They say if falling inside the cocked head, they don't assume, and we don't assume, that the position is random. What's random are the errors, not the ship. So they phrased it incorrectly. Why did they teach this? They used to teach this. They discovered this, and they used to teach this to every navigator in the British Navy in order to tell them that they should not trust the triangle, that the probability that your ship is in the triangle is only 25%. Most of the time, 75% of the time, it will be actually outside the triangle. But they still couldn't resist. And the second paragraph is kind of funny because they say in the practice of navigation, when you get a cocked head, the assumption you make about the position of the ship is the most dangerous part of the triangle, the shallowest or the one that's closest to the rocks or whatever. That's kind of weird because what they really meant to say in the 1 in 4 chance is that you shouldn't trust this triangle at all. But still, people go to the triangle. What do you do with the triangle? Okay, that's it. So you look at this and you say, can you prove it? So why don't you, I'll give you a minute to copy this drawing and see if you can prove it, whether you think it's correct, incorrect. It's not that difficult. The fact that I couldn't prove it should not deter you. I really didn't do well, and you see later, it's not that difficult. Okay, so take a look, see whether you can see why the probability that the triangle contains F, the ship, is only 25%, exactly 25%. And also you have to formulate an opinion. Do you think it's correct or incorrect? It's kind of correct, but not completely. Okay. Yeah, I don't know how you run these Zoom classes, but if somebody knows the answer, at least you can brag that you can't really type the proof in the chat, but if you want to say that you know how to prove it, you can open the chat window and tell everybody else. I don't see it, I don't know why, but I'll keep it closed. Okay, so the next step in this story, the next part of this story happened in 1947 in this paper called Statistical Theory of Direction Finding Fixing by a guy called Stansfield. It's actually an important paper. He published this in an important journal, and the paper is considered kind of seminal paper, important paper. And it's considered important because that's the first paper in the literature that takes the problem of locating an object, location estimation, and phrases it in terms of as a statistical estimation problem. Up to that point, most of the discussion was like in this navigation book, it was a navigation problem, not a statistical problem. They started to think about probabilities, but they didn't see it in terms of modern statistics, mathematical statistics. And here, this is the first time where it says, this is a problem in mathematical statistics, and I'm going to show you some things about this. And the main part of the paper, which I'm not going to talk, is really a geometric formula for the maximum likelihood estimate of the position of the target, the ship, given the three rays. So he makes some assumptions in this diagram. So I blew up one of the triangles. So he shows up. Sometimes the maximum likelihood is inside, outside, and then he shows different combinations to give readers a sense of where in the triangle the target is for different shapes of triangles and different shapes of triangles. But this is not the part that we care about. We care about this paragraph. So he goes back to the probability of the true position lies inside the three line, the triangle at the cocked hat. And he repeats this, and this is all kind of important. He's saying that the odds are 3-to-1 and so on. I won't read the entire thing, but I'll put up a rephrasing of it. And what he's saying is basically that paragraph is the statement of a theorem in which he says that if the error angles have a zero median, then the probability that the triangle contains the target is 1/4. So what he's saying is that it doesn't matter whether the errors are distributed as Gaussians or exponential or whatever, as long as the probability of being clockwise or counterclockwise is the same, which means that the true position is the median, or the true direction is the median, then the probability will be 1/4. And it doesn't give a proof, it just gives a citation. I'll go back, so you can see that at the end of the first sentence, he gives this citation 6, which is to the Admiralty navigation manual. So he says that the odds are 3-to-1, and then he elaborates the conditions of the theorem in words, but he doesn't give a proof. Okay, so that's the first time that this was formulated correctly as a likelihood, and also more mathematically in terms of zero median and so on. And that continued in 1951 with another paper that's kind of important by a high caliber statistician, Daniels. He was the president of the Royal Statistical Society in the UK in the 1970s, 20-something years later. And they actually worked together. If you read the notes at the end, this was a paper that it says read before the research section of the Royal Statistical Society. There were at the end there are questions and answers, and Daniels answers, and Stansfield all ask some of the questions. And Daniels says, or one of them says, that they had the opportunity to work together during the war. So these results were these were not results from the late 40s and 50s. These were World War II results that were getting published after the war in 1946, 1951. And in this, I was attracted to this paper because here he makes it even more clear what the statement is. And he says it's remarkable that there exists distribution-free confidence regions. So now he gives this shape, a more technical name, confidence region. You get a region and you get a confidence likelihood that your target is inside. And then he says incorrectly that Stansfield quotes a statement proved in the navigation manual. Stansfield quoted, but it's not proved in the navigation manual. And then he goes on to say that he is claiming an extension to n lines, and that extension, the probability of being inside the largest enclosed polygon down below is, you can see that it's 1 minus an exponentially small probability. So if you have more than 3 lines and your ship is, then the probability that your ship is not in one of the unbounded infinite regions is getting small very, very quickly. So if you have 5, 6, 7 lines, then your ship will be in with high probability inside the largest enclosed polygon. And this kept being propagated. So this was a neat problem. A lot of people thought it was neat, and it kept propagating. Now, I discovered it not in those papers. I didn't go, I mean, how would I find these papers? I had to get a citation from somewhere or to start searching for the problem. I learned of this from a 1912 popular science book by an author who wrote a lot of interesting popular science books, Mark Denny. And I liked the book. Although here in this particular section, I think he didn't do a particularly good job, but the book overall is very nice. And he repeats the claim that it can be shown from elementary statistical arguments that the probability of the ship being inside the cockpit, you see, it's popular science, but he's careful about the statement of likelihood as opposed to probability is 25%. So this was the first thing, the first time I learned of this problem. I read this and I said, wow, this is going to make a fantastic little exercise for the course and for the book for 2 reasons. First, it forces the reader or whoever solves it to really understand the notion of likelihood and to understand that the random quantities are the errors in the measurements, not the position of the ship. It's very tempting to say that the probability the ship would be inside, outside. These are wrong statements. And it also shows that you can do useful statistical inference that relies on a very incomplete knowledge of the distribution of measurement errors. You don't have to assume it's Gaussian. You don't have to assume even that it has a variance, finite variance. It's nice because when you teach estimation, you're forced, not forced, but you tend to assume again and again that errors are Gaussian because it makes things nice, and it leads because it needs to least squares, and least squares are the problems that we can solve best. So I thought these 2 things, it explains likelihood, or the student would have to understand likelihood to solve it, and it shows that you don't have to assume that things are Gaussian or whatever. But then I had to solve it first. Okay, I can give the. I mean, I once did this. It was also an interesting exercise to me of what would happen, but I felt I had to solve it first. But I couldn't. I failed. So we were still in the Schreiber building, which we shared with math. So math and statistics. So I went up the stairs, talked to one of the statisticians, thought it would be an easy piece. What the statistician told me is that these improbability, these innocent looking problems are sometimes very hard. I didn't want to work on this. So I thought, okay, at least I'm a computer scientist, the least I can do is try to see the computer science way, whether this is at least true or not. And I ran simulations. Of course, when you run simulations, you can't be distribution free. You have to choose the distributions. I chose 2 distributions. And I was lucky enough not to test this hypothesis, but a stronger one that was already also repeated in the popular science book by Mark Denny. And this is it. So the formulation I tested, or the claim that I tested, says that the probability of being inside the triangle is 1/4, but also the probability of being in an unbounded region with two sides is 1 in 12 and 3 sides 1 in 6. This appeared in a little paper in 1991 that starts. There is a BBC Open University statistics. So you see, it was in the popular in the 8 years ago. It appeared in a book, but in the 1990s or 1980s, it was already in a undergraduate curriculum of the Open University in the UK. And like I said, Mark Denny repeated this exact diagram, and that's the one I said, okay, 1/4 I can understand, but where would 1/12 come from? So I simulated this. And, I simulated this, and I discovered it's wrong. Now the guy, and I kind of tried to be entertaining, the guy who wrote this little article, letter to the editor, or whatever, he was not a mathematician, he was not a statistician, he was not a computer scientist, he was a navigator, a professional navigator, but a highly respected one. He was the president of the Institute of Navigation in the UK, and he was also the chief navigator of El Al for a while in the 1950s. So he helped El Al set up their navigation scheme, whatever, to get this, to make sure that the airplanes get to where they need to go when it was still hard. And I'll show you the BBC Open University video a little later. It's kind of nice. Okay, so I did simulations, and I discovered that the 1/4 seemed right, came out 1/4 in my simulation, or close, but the 1/6 and 1/12 were clearly wrong. So Williams seemed wrong. And I later, unfortunately, first did the simulations, and then I searched more on Google for these papers, and I discovered that it was already known that Williams was wrong. 1993, 2 years later, a real statistician published an article in the same Journal of Navigation saying that I shall demonstrate with specific distributions that the 1/6 and 1/12 are incorrect. And interestingly, he says that the 1/4 value for the true position is of course correct. Okay, that's also kind of that statement itself is not completely correct, but that's what he said. Williams replied to this with a letter to the editor, and then the editor decided that if the authors of papers that are clearly incorrect are replying, then he should cut the discussion, and wrote a single sentence after that saying that this is the end of this discussion, is this journal. Okay, it was right. That was a good idea. Okay, so Williams was wrong, but is the 1/4 correct? I didn't know. So I asked Gil Kalai to help me. And he suggested that I write to a mathematician called Imre Barani, which I did. And then Imre and Bill Steger discovered counterexamples to the 1/4. So the 1/4 itself is not correct, or at least not always correct. And then together we decided to continue working on this and find a condition under which it is correct. And we discovered it, and we are now writing the paper. He's working a lot, and I'm slowing him down. And we also proved Daniels's generalization. And what we discovered is that they hold only for distributions that guarantee with probability 1 that the rays intersect pairwise, that the rays must intersect. And if you think about, a lighthouse to the east and a lighthouse to the west of you, the rays might not intersect. That's not always, maybe these are not good measurements, but the rays don't always intersect. And interestingly, it doesn't even hold for the conditional formulation. So if you say, if the rays intersect, then what's the likelihood? Not necessarily 1/4. So the statement really needed corrections. So I won't show you the details of this. The proof is kind of geometric and complicated. That statistician was absolutely correct, saying that sometimes these problems look innocent and easy, but it's not easy. So I'll skip over this, but I will show you the proof of the 1/4, because it's kind of fun and it's just 1 minute. So I think I have time.
We can't hear that.
Okay, so I'll skip a little bit. I'm sorry, I don't know why you can't hear that. I'll just show you the proof. So basically what they're doing is they're drawing the lines, and then they're moving, you move one of the lines deterministically. It doesn't matter, that doesn't have to be probabilistic. And then you move one of the lines, and then you move the 2 other lines. And you realize that once you moved one line clockwise, let's say, here it's clockwise, then the 2 other ones have to move in a I think here counterclockwise for the target to be in the triangle. So now for the other ones, you have 4 possibilities: clockwise, counterclockwise, and you find that only one of them, the ship would be inside the triangle. It's really too bad that you can't hear the presenter here, because at the end she says, and that's always true, which is okay. Okay, so sorry about that. I really like the video. Anyway, okay, so let's move on to a more modern problem. I still have 15 minutes. And that problem is GPS without time of departure. It's also called snapshot positioning or time of arrival, snapshot positioning or course time navigation. So what we have here is what you have up here is the GPS. Second. What we have up here is the GPS equations, and what it says is that the time of arrival, TI, equals the time of departure. D is departure, TDI, I is the number of the satellite, the index of the satellite, plus the distance between me and the satellite divided by the speed of light, plus an offset, plus a measurement error. Where's the offset coming from? It's coming from the fact that my clock is incorrect. Might be a second late, a second early. It's not completely correct, but it's incorrect in the same way for all the satellites. So this is a common bias, sometimes called, or a common offset. Doesn't have the I, the index. There are cases, especially in wildlife tracking sea turtles, tracking bats, in which it's useful to record the GPS signals for a very short period, a few milliseconds, and then you can try to solve this, but you don't know TDI. TDI takes 6 seconds to send, to transmit. The satellite's transmitted, so your phone knows TDI. A GPS on the back of a sea turtle doesn't know TDI, so it needs to solve this some other way. What do you know about TDI? What we know about TDI is that it's a whole millisecond. It's an integer unknown as opposed to a continuous real unknown. And that allows us to determine it precisely. And the fact that it looks like we have, if we have 6 satellites, we'll have 6 transmission times plus 4 other unknowns, the XYZ location and the clock offset. Can we solve this? If the TDIs were continuous, we wouldn't be able to solve this, but because we know that the satellites transmit on millisecond boundaries, this is solvable. And the overall strategy is to use a coarse knowledge of the location and of the clock offset, and then to resolve the TDIs, or really the differences between TDIs, and then to continue as usual. And to explain that, I need to first explain a more important algorithm called RTK, real-time kinematic. It's a way of solving the GPS locations, not from the equations I showed, but from nearby equations, similar equations, in which what you write is that the distance equals some whole number of wavelength, which are 19 centimeters, plus a fraction. And you can measure the fraction very, very accurately to within millimeters or less. So what you get, the observation, is just a fraction. You don't know n. So you don't know how many whole wavelength of 19 centimeters there are between you and the satellite, but you know that the fraction might be 7.5 centimeters. And there is a way to solve, called RTK, to solve for these n's, and then for the location to get centimeter level accuracy. This is an RTK, relatively inexpensive RTK receiver, GPS receiver outside my house. And you can see that I placed it in the intersection, or the T intersection of these parking lot lines. And then I went to the Tel Aviv GIS system, the mapping system of the municipality of Tel Aviv, and drew the point that I got from the GPS. And you can see that it's at the intersection. So it's clearly more accurate than maybe 5 centimeters. And that was within seconds with a relatively inexpensive RTK receiver. It's really a phenomenal technology. How does it work? You linearize the problem. because there are no non-linear solvers for mixed integer least squares. Then you eliminate all the real unknowns, and you have to do this using something called unimodular transformations. In this case, they're very easy. There are subtractions. So they are non-orthogonal. You have to correct the least squares to move to generally least squares to preserve the maximizer. And because it's unimodular, it preserves the integer solutions. And then you do 3 steps. A QR step to reduce the coefficient matrix to a triangular form. You transform R using a lattice basis reduction, a Lenstra-Lovász algorithm, so that the diagonal of the triangular matrix doesn't decay too quickly, and then you search for the exact maximizer, for the exact minimizer. And these parts 3, 4, and 5 together are really an exact solver for a problem called CVP, the closest vector problem in a lattice. It's NP hard, but in practical cases, it's solvable even on embedded hardware today. So going back to the course time real-time navigation, there is an algorithm for this. It has nothing to do with RTK. It's an algorithm called course time navigation. It was proposed by a very productive GPS researcher called Frank van Diggelen. And he specifies the algorithm completely, but doesn't explain many important quantities and properties. And it's been used in at least 10 other follow-up papers by others. They always give the same mathematical expressions, saying that it's explained by Van Diggelen's book. It's specified in Van Diggelen's book, but it's not explained there. And I don't have time to go over the algorithm. What are missing, the gaps are, first, can you linearize? You're linearizing an equation in which some of the variables appear in the nonlinear part. So TDI is an integer parameter that appears in the nonlinear part of the expression. Can you linearize? What does it mean? I mean, you can't derive an integer, right? You can't differentiate an integer, sorry. And then the other oddity is that the unknown O is supported or represented by 2 corrections in the linearization. One for the sub-millisecond part and one for the whole millisecond part. And it even gets weirder because the whole millisecond part you solve for, but you don't constrain it to be an integer. So there is an algorithm, but it's not explained completely. So I felt that because I taught RTK, so RTK also was kind of hard for me to understand, but once I understood it, I said, okay, this cannot be that different from RTK. So let's try to formulate this in the same way as RTK, as an integer least squares CVP problem. And Eyal Wasserman, one of my students, and we did it. What did we do? We formulated the problem step by step, starting from the nonlinear as the original nonlinear observation equations. We showed what's the error that you incur when you linearize them. That's kind of known in GPS. It wasn't known to me, but it's known. Then we enumerated all the approximations that you do along the way. You do a couple of approximations, not one. And then we derived from these kind of first principles Van Diggelen's algorithm. And once you do that, you immediately discover that there is a way to improve its robustness a little bit. Because when you understand where it's coming from, you understand that you can do this better. And then the most, I think, interesting part for me was that we were able to generate an RTK-like formulation of it that solves, that's more expensive than Van Diggelen's. Van Diggelen is basically a rounding solution to the integer linear problem, integer problem, not exactly, but close. And by doing this, we can also solve with only 4 satellites overhead, not 5. He had this two correction terms, so he needed 5. Also, everybody else will solve this. And also, what's more important is that the ILS formulation converges with much larger initial errors. There are other ways of doing this. So in terms of practical significance, I don't think that this will be better than the state of the art, but it is a more complete description of all the design space of these algorithms and all the errors, the approximation errors that they incur along the way. If you're looking for a research problem, this is an interesting problem in theory or something close to theory. because this is an NP-hard problem that people solve routinely all the time on problems that are not huge, but also not that small, and it's solvable all the time. The other part that's more interesting is that you can solve this without the basis reduction, but it runs sometimes very, very slowly. So the branch and bound search that's supposed to be exponential, you really see that it's exponential. Once you run the basis reduction, it really cuts down on the exponential part of the algorithm, and it's not so clear why. What is the objective function that you're trying to reach in the reduced lattice or reduced representation? And what's also interesting is that people found out that LLL is not optimal for speeding up the exhaustive branch and bound search, but that you can simplify LLL and it still works just as well, or sometimes even better. So finding out what's the objective function that should be pursued there is interesting. There people made some conjectures, but at least some of them that have been made in the literature are clearly wrong, like trying to conditioning, improving the condition number of the basis. That's not true. Okay, so I'm almost done. We've gone through the research to more research, and then to a course, and then to more research. And I want to offer 4 thoughts in the 4 minutes that I still have. The first one is that when you go out of the computer science algorithms literature and you read algorithms literature in other areas, like this algorithm by Van Diggelen, is an electrical engineer. Like I said, a very productive, talented one. You read the algorithms and you discover that they're not really specified as fully as we are used to specifying them, the conditions under which they work and so on. They're kind of under specified or under described. But I think the first order thing you have to say is that discoveries are discoveries. You have to give the British Admiralty and Daniels and Van Diggelen credit for these discoveries, even if they didn't make them or state them and prove them as rigorously as many of us, I think, are used to. The flip side of that is that the informal arguments are really dangerous. I mean, it's a cliche. We know this. This is why we teach rigorous mathematics in the undergrad year of computer science and the freshman year, and sometimes in follow-up courses. But it really is true, and you discover this again and again, that people make informal arguments, and they sometimes they're incomplete, they're wrong. And the ability of incomplete, sometimes incorrect results to propagate is just incredible. They can persist for decades. And I'm sure people will continue to cite the incomplete statements well after we publish, Imre Barani and I and Bill Seger publish the correction or the complete statement. Okay, so the second thing is that what happens when you create a new course is that you have to organize the body of knowledge. You have to define its scope. Sometimes it's already defined. Sometimes you have to redecide decide for yourself what's the scope. And at least for me, you always have to explore it to learn the bits that you don't know. And I've developed 4 courses, or I taught 4 different major courses in my career. And every time I had to explore it to learn the bits that I don't know. And sometimes to rephrase it. And for example, in my book, kernel filtering, if you look at it, I think to most computer scientists, including people in numerical in algebra, it's incomprehensible. There are several formulations in the electrical engineering literature. To most of us, it's incomprehensible or very, very difficult to understand. But somebody, not me, Duncan and Hoare in the late 60s and then in the mid 70s, Page and Saunders already reformulated this in a very little known paper that shows that it's really just linear least squares, and you can find not the algorithm, but there is an algorithm that's actually more stable, better than all the other variants of Kalman. That's basically a sparse QR factorization. So that's a rephrasing that's very easy for a new audience, including me and my students, to understand. When you write a book, you go through the same benefits, but more so because you can't correct and explain yourself at real time. It has to be clear from the text without you saying, oh, yes, I didn't think about this, I didn't explain this, and so on. At least you try. At least I find this very rewarding professionally, even if in the usual metrics of papers and citations and so on, it doesn't count in the same way. But personally, professionally, it's very rewarding, this process. The last thing I want to, almost the last thing I want to say is that we teach algorithms often without the applications. Sometimes we don't have a choice. They require too much background or too much time. But when you can teach algorithms and motivate them with the applications, I think the experience is fantastic. It's more fun. It's more interesting for us, for the students. In some areas, I think it's already being done because it's also natural, like computer vision, because again, it's geometry, 3D geometry. It doesn't require background in business or finance or chemistry or biology. But when you can do this, it's important. And the other thing I discovered through teaching this course is that modeling how to turn a technical story, a diagram that students already understand fully into mathematical expressions that you can then apply an algorithm to is hard for students. They're not good at this. We think about applied mathematicians as the people who need to do this, or engineers or scientists, but our students sometimes do need to do this. And when they do, it's hard. It's harder than sometimes the algorithms parts that we focus a lot so much, which is important. That's our job, to focus on the algorithms, but the modeling is also important, and it's surprisingly hard for students to do this well. The other thing I discovered, kind of community, is that publishers are looking for good books, for high quality books, for this series, this publisher, other publishers. If you want to write a book, I encourage you to do that. Some of you shy already did that. That's great. And when you weigh the pros and cons, yes, you will probably publish a few, maybe a little fewer papers. It may cost you 4 papers or 10 papers. I don't know. But there is an opportunity for professional growth. And also, I think the relative delta impact in citations and recognitions is not really comparable. It may be a good deal. I'm not saying you should wait it for yourself, but that's it. Okay, thank you very much for attending. Come visit us. Now you see what computer scientists do in Tel Aviv.
So let's thank our speaker. I guess whoever wants to turn on the microphone can. Unfortunately, I think we're a little bit out of time, so we may not have time for questions, but again, thank you very much.
Okay, bye-bye. I'll stay here. When you close it, you close it. If people want to ask something or to say hello, that's great. If you have to go, completely understood. Thank you very much for inviting me. It was fun.
Thank you. So yeah, actually, if anyone wants to ask, I mean, if anyone needs to go, feel free to go. But if anyone wants to ask questions, the room is open. So you can just go ahead and do so.
Sivan, I have one question, if it's okay.
Sure.
You said about the cocked hat problem that it's better to look at that it's wrong point of view to look at the probability that the ship will be in the triangle, and we need to see if the probability that the triangle includes the ship. It's just out of the notation of maximum likelihood that we try to fit the parameters for the data, right? That's the reason you said that.
Yes. What you're trying to estimate, the expression you're looking for is of the likelihood of the probability. Yes, the probability of a result given the observations. Yes.
Oh, great. Thank you very much.
Random. The important part is what's random is not the position of the target in these problems. You assume this is deterministic, classical estimation. You assume that the unknowns that you're trying to estimate are numbers, fixed numbers. You get measurements. The measurements have errors in them. That's where the probability is. And when you translate this into this number, it's called a likelihood in statistics, not a probability.
Great. Thank you very much.
Okay. Bye-bye.
Goodbye. So I'm going to close the meeting now.
Yes.
Thank you very much.
Thank you very much.